Hello class, I hope everyone is doing well. Welcome to our Calculus 2 lecture for Wednesday, April the 8th. So probably by the time you watch this video, the test number 2 will already be posted. And hopefully you've already opened that and are working on the solutions to test number 2 so that you can return those to me by email right by Friday, April 10th at 1 p.m. Okay, I don't have really much to say currently now about the test since that's already underway. Remember last time in the notes, in the lecture, we began talking about trigonometric substitution, and so we have a couple of more examples to do with trigonometric substitution today. And so we'll work through those examples. The homework for trig substitution is posted here. That's this section 8.4, and that is due next Wednesday, a week from the day this lecture is posted, right on April the 15th. Some of the problems on that homework are going to be challenging for you, I know. So although it's not a long homework, the individual problems themselves are lengthy. So this homework can be a little bit time-consuming to do the problems on this homework. And today we're going to start a new topic. We have finished integration techniques, so trig substitution is going to be the last integration technique that we'll learn in the course, but we're not through with integration. We're still going to be doing different types of integration forward in the course, but our last special process that we learned for finding an antiderivative, right, for carrying out, for evaluating an integral, that's finished here with trig substitution. Okay. Remember, as usual, right, you can visit me during my Zoom office hours, right, and so you can find the announcements on Blackboard and here in WebAssign, right, on how to connect to those sessions. So don't forget about those opportunities to ask me questions. And also, of course, as many of you have, you can log into Taylor's Zoom SI sessions. I hope you were able to log into her session on Monday, April the 6th, so that you could get help for the test. Okay, so we're going to go ahead and launch into the lecture notes now and look at the last couple of examples from trig substitution. The first one is going to be probably the toughest example that we look at, but then I'm going to show you a shortcut that's really useful in carrying out trig substitution. It's really formulas that sort of condense the steps for trig substitution and make certain integrals where normally you would use trig substitution much easier to carry out because we have formulas that will allow us to write down what the antiderivative is going to be without actually going through all of the trig substitution steps. Okay, so that will be the last example, and then we'll start with our next topic. Okay, so let me switch to the notes here. That's the wrong notes. Yeah, here we go. Oh, before I do that, I want to go ahead and close. Let me close Chrome here because that eats up a little bit of my CPU power. All right. Okay, so here is the here's our next example in trig substitution. So notice this is a definite integral. And so that's going to make it already more complicated than the previous examples. And but the trig substitution in this problem also is maybe a little bit more complex than in the prior examples. All right, so we want to evaluate this definite integral, right? This is a definite integral. So notice at the end of this process, we're going to come up with a numerical answer, right, to the problem. But, of course, to evaluate the definite integral, we need to find the antiderivative first, right? So that's the first step of this process. And then once we find the antiderivative, right, we'll plug in the limits of integration, right, into the antiderivative. But first things first here, let's just worry about finding just the indefinite integral, right, just the antiderivative of this expression square root of x squared minus 3 over x, right? And you can notice almost immediately, right, that looks like it might be a good candidate for trig substitution because it involves this square root, right, in this case of the difference of two squares. Of course, x squared is obviously a perfect square. 3 is not a perfect square, right, but we can certainly think of it as a perfect square because 3 is the square root of 3 squared, right? So, I already see here my value for a, right? That's usually what we label that constant, right? That we're squaring. When we do trig substitution, we usually label that a, and we can already see, right, that a is going to be the square root of 3, right? Because of course that means that a squared would be the square root of 3 squared, which is 3, right? Okay, so since we have difference of two squares here, or the square root of difference of two squares, right, that suggests that we might use a trig substitution, right, to find this antiderivative. So let's go back here and look at our table. So I have to scroll way back up here in the notes, but here it is. So let's look at our table that suggests, right, the correct trig substitutions in different situations. And here's the situation that we're dealing with, right, in this problem. We have difference of two, square root of difference of two squares, but notice in this square root, right, the expression is squared, and then it's minus the constant squared, right? Notice in this first trig substitution, it's constant squared minus expression squared, but here we have expression squared minus constant squared, and this is exactly the situation, right, that we had in that example, because that example, remember, the integrand was x squared, square root of x squared minus 3 over x, I believe, right? So in that square root, we do have expression squared first and then minus constant squared second. So the correct trig substitution we're going to make here is we're going to let u be our constant a, right, which we already discovered was square root of 3 times secant of theta, right? Okay, so this is the trig substitution that we want to make in our in this example, a secant theta, So let's remember that, right? A secant theta is the substitution that we're going to try here. All right, let's write that down, actually, so we don't forget it. So that is the substitution that we want to make. Okay, so we already know what a is, right? A is going to be the square root of 3. Let's go ahead and make a preliminary substitution here, as I normally do, right? Let's change our variable from u to from x to u, although that's kind of a little bit meaningless in this problem to make that substitution. It's not really really necessary, but let's go ahead and do it just to be formally correct here. So I'm going to let u be x, since the expression that is squared in this difference of 2 squared is just x, right? X squared. So I'm going to let u be x, and then of course that means that du is just plain old dx, right? And so we know how to get rid of the dx as well. And so let's see. So I end up with the antiderivative of square root of u squared minus, right? Remember, this is square root of 3 squared, right? That's what 3 is. And then all that divided by x, but x is u, right? And then remember, du is dx, so I can replace the dx by du. Okay, now it's clear how we're going to make our trig substitution, right? We're going to let, for u, we're going to substitute a, which is square root of 3 times secant of theta, correct? Now, before we make the substitution, let's go ahead and draw our representative triangle, right, that kind of illustrates this substitution that we're making, right? And remember, this triangle may serve us later in the problem, right, when we're trying to undo the substitutions that we've made here. So remember, I'm just going to draw a right triangle here. This is supposed to be a triangle. That bottom edge does not look very straight, right? So let me redraw that. So here we have a triangle, okay? And that's a little bit better. And we're going to embed this angle theta, right, as one of the acute angles in the right triangle. And now, remember, because u is going to be a secant theta, right, which is square root of 3 times secant theta, that means that the secant theta is going to be u divided by square root of 3, right? If you take both sides of this equation, right, and divide by square root of 3, you get secant theta is u over the square root of 3. So let's draw that into this picture. So secant of theta, well, secant is the reciprocal of the cosine, right? Remember, secant is the reciprocal of the cosine. So cosine is adjacent over hypotenuse, so that means secant is hypotenuse over adjacent, right? So the hypotenuse here must be u, right? And the adjacent side of this triangle must be square root of 3, correct? And now if you use the Pythagorean theorem and solve for the opposite side of theta, you will get that the opposite side of theta is exactly this expression. It's going to be the square root of u squared minus the square root of 3 squared. Okay. All right. So we want to keep that in mind when we are. We want to keep this representative triangle in mind for later in the problem, right? Okay. Now, well, let's see what happens now when we make our substitution for u. So we're going to get kind of a big mess here. Oh, before I make the substitution for u, right, I need to compute what du is going to be, right, because I also have to substitute for du, right? So let's come up here and differentiate both sides of this equation with respect to theta. So I'm going to write down du d theta. What is du d theta? So what is the derivative of square root of 3 times secant of theta? So you're going to have to remember what the derivative of secant of theta is. And so that is secant theta tangent theta. So I hope you recall that, right? The derivative of the secant. We don't differentiate the secant all that much, right? But the derivative of the secant is secant theta tangent theta, okay? And that means then that du, if you multiply both sides by d theta here, right, you'll get that, let's write this down, so we'll get that du is equal to square root of 3 times secant theta tangent theta times d theta, right? So we're going to have to remember this in just a second, because we're getting ready to substitute for that, right, in this integrand. All right, so let's see if we can write all this out. This is going to be a mess, right? So u squared, u is square root of 3 secant theta, and that's squared, minus, okay, well, square root of 3 squared, of course, is 3, right? So I'm just going to keep writing that as 3 now. All right, and then all divided by u, but u is square root of 3 secant theta again, right? And then times du. But so here's where we use the du, right? That's square root of 3 times secant theta tangent theta d theta. Woo! Okay, so that looks like right now like a big mess, right? But and that's usually what happens at this stage, right? After you have made your trig substitution, you get what looks like a really awful integrand, correct? But now, through the magic of trig, if we have chosen the correct trig substitution, through the magic of trigonometry, hopefully your integrand will simplify. All right, well, I hope that's the case. All right, so let's see what really happens here. Otherwise, maybe trig substitution is not the way to go here, okay? And you know, sometimes trig substitution works beautifully, and sometimes it doesn't. All right, so let's see. We have square root of, well, square root of 3 squared. That's 3, right? And then you have the secant squared, right? So you have secant squared theta minus 3, right? And then, let's see, what's in the denominator here? Well, now things are starting to look up, because look back in the prior line, we're multiplying by secant theta, but we're also dividing by secant theta, right? So we can divide out the secant theta, okay? So that is nice. So now I have square root of 3, right, just in the denominator. So you see, things are already looking up. And oops, no, I don't even have the square root of 3, do I? Because, I forgot. Here I have a factor of square root of 3, and here I'm also dividing by square root of 3. So actually, the square root of 3 is gone as well, right? Oh, so things are getting a lot better fast, right? So actually, there's not even a denominator here anymore. That's cool. So I just have this square root times, well, what's left there now? Just tangent of theta d theta, right? Okay, so see, things are indeed, the situation is indeed improving. Now, the whole point of doing, remember, of doing one of these trigonometric substitutions, okay, and so I don't know who first had this idea. It was a long time ago, but I don't know who first came up with this trigonometric substitution idea. But the whole point of doing the trig substitution is to eliminate this square root, right? We want to get rid of that square root. And let's see now if that is going to happen. Well, look, from both of the terms underneath the square root, right, notice you can factor out a 3. So I'm going to factor a 3 from this term and a 3 from this term. So you get square root of 3, and then you have secant squared theta minus 1, right, times tangent theta d theta. But now here's where our trig now identities come in handy. Remember, secant squared theta minus 1, right? Remember from one of our trig identities, you know sine squared x minus tangent squared x is equal to 1, right? That's the second Pythagorean identity. So what that means is, if you rewrite this, I'm sorry, this is, I wrote that trig identity wrong, right? This is secant. Secant squared x minus tangent squared x equals 1, right? So if you rewrite this equation, you can see that secant squared of x minus 1 is equal to tangent squared of x, right? Just rearrange terms in this equation. And so all of this is really just, all this secant squared theta minus 1 is really just tangent squared of theta. So see there, now we get this nice simplification. So I have square root of 3 times tangent squared of theta times tangent of theta, again, d theta. But now this square root, you see, you can simplify because you have square root of tangent squared, so that's tangent. So you end up here with square root of 3, right? 3 is not a perfect square, so I can't simplify its square root, but I have square root of 3. But tangent squared theta is a perfect square. So that simplifies to tangent theta, and then you still have this other factor of tangent theta, right, times d theta. So look, nice here. We just have, I can factor out this, the square root of 3 is a constant, so I can factor that in front of the integral sign even. So I have square root of 3 times tangent squared theta d theta. All right. So see, the situation is now looking up a little bit. However, now I'm faced with still a kind of formidable antiderivative. I have to figure out what is the antiderivative of tangent squared theta. Now, if that were just antiderivative of tangent theta, I would know that because we know the antiderivatives of all of the trig functions, right? Okay, but this is tangent squared theta, which is a little bit a tougher thing. All right, well, it's not, okay, because now we are going to rely on our trigonometric, our Pythagorean, our second Pythagorean identity again, right? Because that tells me that tangent squared of theta, right, is, remember, that's secant squared of theta minus 1. So I have square root of 3 times secant squared theta minus 1 d theta. Now you may wonder, okay, why bother, right? You know, why do I want to go from tangent squared theta to secant squared theta minus 1? I still would have to integrate secant squared theta, right? So, you know, how has that improved my, how has that improved the situation at all? Okay, well, let me show you why. All right, so I'm going to break this up into two antiderivatives. All right, so I have square root of 3 times the antiderivative of secant squared theta minus square d theta. Let me not forget to put the d theta here. D theta minus a square root of 3, and then antiderivative of just 1, right, times d theta. But I know what the antiderivative of secant squared theta is, because the derivative of the tangent is the secant squared, correct? So the antiderivative of the secant squared, so nice there, is just tangent of theta, okay? And what is the antiderivative of 1? Remember, this is with respect to theta, right? So the antiderivative is just going to be theta, right? Like the antiderivative of 1 dx is x, the antiderivative of 1 d theta is just going to be theta. So you end up here with, I'm going to factor out the square root of 3 from both of those terms. So you have square root of 3 times tangent theta minus theta. There is the there's the antiderivative. Remember, I don't have to add the constant here, right? I do not have to add the constant because this is part of a definite integral, right? So I'm going to use this antiderivative in a moment here to evaluate the definite integral with the limits of integration. So I don't need to write the plus constant. Now, however, we do have to undo our substitutions, right? So I have to replace theta, right, with u, and then I have to replace u with x. Well, replacing u with x is easy, but let's see how we're going to replace theta with u. And this is where the this is where our representative triangle right now is helpful. So I need to figure out what is the tangent of theta, right? So let's look back up here and see if we can figure out what is the tangent of theta. Well, remember, tangent of theta is what? That's opposite over adjacent, right? So the opposite side we know here now is square root of u squared minus, well, square root of 3 squared is 3. So we have square root of u squared minus 3 over square root of 3. So there's tangent of theta. Now, what is theta, though? Okay, because I also have to replace theta, right? So what is theta? But remember, let's come back here, right? Remember, secant of theta, look back here. So remember, secant of theta was u over square root of 3, right? So now you can use your inverse trig function to solve this equation for theta. If secant of theta is u over square root of 3, that means theta is arc secant, right, of u over square root of 3, correct, right? That's just using our inverse trig functions, right, to solve this equation. So, see, we know what tangent of theta is now in terms of u, and we know what theta is now in terms of u. So that's what I have to substitute in here now for these two things, right? Wow. Let's see if I have room even to write that down. So I get that what I have square root of 3 times tangent of theta. Remember, that was the square root of u squared minus 3 over square root of 3, and theta was the arcsecant of, what was it? It was u over square root of 3, correct? All right, so there I undid my substitution. I've undone my substitution, right? I've replaced theta now by u. Now I have to replace u by x. But that was easy because remember, our original substitution was just u equals x. So wherever I see a u here, I can just replace that with x. So here's my final expression for my antiderivative, right? But I'm not through with the problem. But now I know what the antiderivative is. It's square root of 3 times x squared minus 3 over square root of 3 minus arcsecant of x over square root of 3. Okay. Now, what do I do with that antiderivative, right? Ooh, that's a big, ugly antiderivative, right? That now I have to use this, right? I have to use this now to plug in my original limits of integration, right? Okay, to evaluate the final answer. All right, so, well, let's do this here. I think we have just enough room, right? So there is the, all right, let's copy this somewhere so we can, maybe I can copy this somewhere where we can see it. So let me put this back up here. All right, so there's the antiderivative, right? And I have to plug in, correct, my limits of integration, right? I have to plug those in to my antiderivative, right? And then carry out those computations so we can come up with our final value for this definite integral. All right, so let's plug in the 2 first. So I would have a square root of 3 and then what? Times the square root of 2 squared is 4 minus 3 over square root of 3, right? Okay, minus the arcsecant of 2 over square root of 3. All right, and then you subtract off from that, right, what you get when you plug in square root of 3. So that's going to be square root of 3 times, well, let's see, when you plug square root of 3 in for x, well, that's nice. You get square root of 3 minus 3, right? Because square root of 3 squared is 3, minus 3 over square root of 3, and then minus the arcsecant of, let's see, what's that going to be? Square root of 3 over square root of 3, which of course is just 1, right? So we have this minus this. Well, that's a little bit of arithmetic to do, right? But it's not that bad, except for we have to evaluate some arcsecants, okay? All right, so I'm going to do that for you quickly. This is the arcsecant of 1 because square root of 3 is 1, right? The arcsecant of 1, however, if you evaluate that, you're going to see that the arcsecant of 1 is 0. And of course, this term is also 0 because you have the square root of 3 minus 3, which is the square root of 0, right? So you end up here with this is 0 and the arcsecant of 1, just check it if you don't believe me. Arcsecant of 1 is also 0. So this second quantity, all of this is just 0. That's nice. So you're just subtracting 0 here, right? So you can forget about the subtraction. All you have to do is worry about this first quantity, right? Well, let's see. Here we have 4 minus 3, which is 1. Square root of 1 is 1. So you have 1 over the square root of 3, but you're multiplying that by square root of 3, right? Well, Let me write it out. So you have square root of 3 times 1 over square root of 3, because this is going to be just square root of 1, which is 1. And now we have to figure out what is the arcsecant of 2 over square root of 3. Well, again, you can check this, but this turns out to be easy. The arcsecant of 2 over square root of 3 is pi over 6. Okay, so 30 degrees, pi over 6, is the arcsecant of 2 over square root of 3. If you don't believe me, just check that. Okay, so arcsecant of 2 over square root of 3 is pi over 6. So when you multiply in the square root of 3 into the parentheses, you end up with square root of 3 over 3, which is 1, minus pi times the square root of 3 over 6. There it is. There's our answer. That is the right answer, I think. Okay. So finally, right? See, I told you that was going to be a long problem, right? Finally, we can evaluate that definite integral, and we get 1 minus pi times the square root of 3 over 6. Okay. All right. So that's a challenging example of trig substitution, but a powerful example too, right? Of what we can do with trig substitution. All right, let's take a little pause here, and then I'm going to show you. Again, I promised you a shortcut, right, with trig substitution, and so I'm going to show you that shortcut that on certain problems will save you a lot of time. So you want to pay attention to this shortcut and learn to recognize when to use the shortcut, because it can really save you a lot of work. All right, but let's pause here first before we look at that. Shortcut, if I can get my screen to respond here. There it comes. Okay, so let's resume with our last example of trig substitution, and this one is going to be a little bit easier because we have some formulas that we can use to find any derivatives that can be evaluated using trig substitution, but the formulas provide you a shortcut to finding the antiderivative without having to go through all of the actual steps of the trig substitution. And these integrals occur frequently, so that's why these formulas have been developed. All right, so notice they're just very basic antiderivatives here involving square roots, and these are all square roots, right, that fit the pattern of trig substitution. And so again, formulas have already been developed, right, to tell you what the antiderivative is going to be without you having to go through all of the steps of the trig substitution. So if you encounter an integral that fits one of these three forms, right, just plain square root of constant squared minus an expression squared, or square root of expression squared minus constant squared, or square root of an expression squared plus, not minus, but plus a constant squared. So if you have just those integrals that fit just these forms, then you can just use these formulas from this table to write down what the antiderivative is going to have to be without going through all of the trig substitution steps. So, you know, it's kind of messy to go through all those trig substitution steps, as you've seen from the prior examples, right? So you really want to make use of these formulas when you have the opportunity to, okay? So be watching out in your homework, right, problems, if you have a integral that just looks like this, nothing else but square root of difference of two squares, or right, or square root of sum of two squares. Remember, you can refer to this table to find what the antiderivative is going to be, and then just write it down from the table without having to go through all the steps of the trig substitution, right? And so it's a real time saver. So you really want to make use of this table when you can, right? Let's look at an example of this. So I have to scroll down because I've got an example way down here. Okay, so let's look at this example. And I've recopied the table here so that we can refer to it easily. and not without having to scroll up. All right. So look, this example says find the antiderivative, right, of this square root, right? So it's square root of this expression, 5x minus 2 squared, and then plus 16, right? Okay. So notice that fits very beautifully into this table, right? In fact, into part 3 of the table, correct? Because see, this is just the square root, right, of an expression squared, right? 5x minus 2 in this case is your expression. So this is the expression u, right? Okay. And then plus a constant squared, right? In this case, the constant obviously is 4, right? Okay. Because we have 16 is 4 squared. So that means then that we can just use this formula, right, very easily to write down what the antiderivative is going to be without having to go through all of the trig substitution steps. But this, I want to point out, this formula and all of these formulas were derived from trig substitution. But we, if we recognize that we can use the formula, we don't have to do all of the trig substitution, right? We can just use the formula. Okay, so, well, before we actually use the formula, let's make sure we substitute u for x here, though, in our integrand first, right? So, as I mentioned, right, u is going to be, we're going to substitute u for this expression, 5x minus 2, and that means du dx is 5, correct? Because the derivative of 5x minus 2 is 5, and so that means then that dx is du over 5, right? Okay, that is dx. So let me rewrite this integrand first using u like we have it in the table instead of using x. So again, 5x minus 2 is u, so I'm going to rewrite the 5x minus 2 squared as u squared, okay? And then, of course, 16 is 4 squared, right? And then what is dx? Remember, dx is du over 5. Right? And now this du over 5, you can factor out the 1/5, and so you have 1/5 times the antiderivative of u squared plus 4 squared, right? And then just plain du, right, if I factor out the 1/5. And see, that now fits perfectly into this formula, right? And so I can write down easily what the antiderivative is going to be. It's going to be a big mess, but I don't have to derive this big mess, right? I just have to write it down. So that makes it a whole lot easier, right? So you have 1/5, don't forget that 1/5, and then times what? 1/2. 1/2 is part of the formula. And then let's see, u square root of u squared plus, there's the a squared, so remember that was 16, right? Plus the a squared, that's 16, times the natural log of the absolute value of the u, right? Plus, and then there's our u squared, square root of u squared plus 16 again, right? Okay, and then stop your absolute value, and that's the end of the antiderivative, right? So there it is. See, wow, it's really nice, right? We could just write down that antiderivative from this table without having to go through actually all the trig steps, right, of deriving that antiderivative. Now, we do have to undo our substitution, however, right? So so let's make sure we do that. That means I have to replace the u, right, with x again. Or in this case, replace the u with 5x minus 2, right? So let's see, 1/5 times 1/2, that's 1/10. So we get 1/10 times u is 5x minus 2 times the square root of the 5x minus 2 squared plus the 16, right? Plus, and then now let's write the second part here. So I have 16 times the natural log of the absolute value of u, that's 5x minus 2, plus that square root, right, which was u squared, but that's 5x minus 2 squared plus the 16, right? And that is the end of it, okay? Let me make sure I close all my parentheses correctly here. And then I have to, don't forget, add on. So I have to add on there the constant c, okay? Ooh, there it is. Wow, so easy, right? Well, I don't know, easy is a relative term, right? But certainly easier than having to actually do the trig substitution, right, to discover this long antiderivative, right? So this table of antiderivatives, this table of integrals is a really useful time-saving device for you, right? Okay, all you have to do is recognize, oh yeah, I have an integral that fits into one of these tables. It's just square root of sum or difference of two squares. Nothing else in the integrand, right? Just square root of sum or difference of two squares. And if that's the case, then I can use one of these formulas, right, to write down the antiderivative without having to go through all the steps. Okay, I want to show you now one other thing that's going to come into the homework, and so this is really important. I didn't have an example like this, but it's in a couple of the homework problems, and so I want to point it out to you here really carefully. Look, in a couple of places in the homework, when you're doing the trig substitution, you may arrive at some point with trying to integrate sine squared or trying to integrate cosine squared. And there are some identities that are useful to you in this process, and these come from trigonometry. So if you see sine squared of x, if you're trying to integrate that in one of your antiderivative problems, you can change that to 1 minus the cosine of 2x over 2. And this, it will be easier to integrate. Okay, so remember, sine squared of x is 1 minus the cosine of 2x over 2. And likewise, you can also transform cosine squared of x. Cosine squared of x is 1 plus the cosine of 2x over 2. So keep this identity in mind, or these two identities in mind. These are called the power identities when you are integrating, if you come across trying to integrate sine squared of x or cosine squared of x. Let me show you two other identities that might be helpful to you as well. These are called double angle identities. So if you have sine of 2x, you can simplify that easily as just 2 sine x cosine x. So sine of 2x is the same as 2 times the sine of x times the cosine of x. And cosine of 2x is cosine squared of x minus sine squared of x. I'm not sure if you'll use these double angle identities in your homework. They might come up. But I know that this identity is going to be useful in the homework because I've looked at the homework problems. And I think at some point you will run across having to integrate sine squared of x. And remember, you can change that to 1 minus the cosine of 2x over 2. So please keep that in mind when you're working on your trig substitution homework. Okay, so that's our last example of trig substitution. So now we are going to start with a new topic, okay, which does involve integration, but it's not an integration technique, all right? So we have learned all the techniques we're going to learn in this class for helping us carry out integration. There are lots of other integration techniques we could learn, but I think we've hit the highlights, all right, for this semester with integration techniques, okay? All right, so I'm going to pause again before we resume. Okay, we're back, and we're going to start a new topic now. So, you know, calculus relies a lot on the notion of infinity, but the notion of infinity is a very tricky concept, and it often defies our intuition. And so frequently, problems in calculus will confound our intuition. It will contradict our intuition about infinity and how infinity actually works, and that's really a very fascinating and interesting part of calculus. it can really expand your mind or your conception of what the infinite quantities or infinitely large or infinitely small quantities really, how they really work. And this next topic is going to illustrate that, I think, for us. Okay. So what we're going to study now is what's known as improper integrals, and let me show you an example of an improper integral. And these occur frequently. We have to evaluate improper integrals frequently in mathematics, but in particular in statistics, we are required, in probability and statistics, we're required to evaluate improper integrals. And of course, statistics have been just such an important part of the news lately because of the pandemic, right? And trying to model the course of this virus. All right, so here's the problem that we're going to start with, our first example. We want to know, it's a very typical type of calculus problem, though. We want to know what is the area beneath this curve, 1 over x. So that's a curve that we actually studied right from the beginning of the course, right? What is the area beneath this curve, 1 over x? We're going to start here, the area at x equals 1, but we're not going to put an upper bound on the area. So I want to know what's the area beneath that curve from 1 all the way to infinity on the x-axis. Okay, and so it's very easy to kind of sketch a graph. Well, kind of easy to sketch a graph of this this area right. Here's a picture of it. So this is the curve 1 over x, right? And starting at 1 here on the x-axis, but we want to find what is this red area, but we want to think of the we want to calculate this area all the way out to infinity, right? Along the x-axis, right? So we don't have an actual upper bound for this region. Well, look, when someone asks you that question, what's the area beneath this curve, starting at 1 on the x-axis and all going out to infinity on the x-axis, right? I think your natural response, your intuitive response would say, well, that area has to be infinite, right? That area is infinite because this region is unbounded, right? It doesn't have an upper bound along the x-axis. It extends out to infinity along the x-axis. And so the curve 1 over x, by the way, that curve never touches the x-axis. So this region is unbounded, right? Okay, I mean, this region gets kind of thin as you get further out the x-axis, but it never stops, right? So you have an unbounded region, an unbounded area. So intuitively, right? We would think that the area of that of that unbounded region, that area should be infinitely large, correct? And so I would agree. That's I think that's what most of us would think, right? To start with, okay. But we want to be able to verify that, right? So analytically, that's what our intuition tells us. But we want to be able to verify that analytically, right? That that this that this area should be infinite. Okay, so well, in calculus course, how do we compute areas like this, right, beneath curves down to the x-axis? Well, that's just a definite integral problem, right? Okay, so so you know how to set up that definite integral, right? That area is going to be what, the definite integral of this curve 1 over x, right? Starting at our lower bound on the x-axis, which is 1, right, and then going up to the upper bound on the x-axis. But here's the problem: there is no upper bound, right, on the x-axis. So for this upper limit of integration, there's no fixed value there, right, that we can put for the upper limit of integration, because this, again, this area is extending out to infinity on the x-axis, right? So so we just have to put infinity there, right? Okay, so we're trying to find the area from 1 to infinity, right, beneath this curve 1 over x. And so this is called an improper integral, all right, in calculus. So so what makes an integral improper? It's because one of the limits of integration is infinite, okay? In this case, the upper limit, right, of integration is infinity. And so we're not going to be able to evaluate this definite integral in the usual way, right? Okay, you know, the usual way would be I would find my indefinite integral, right? I would find the antiderivative of 1 over x, right? And then I would plug in my limits of integration, right, and do the subtraction, right? That's normally how I would evaluate this definite integral. But since my upper limit of integration is infinity, right, that process is going to break down, right? I'm not going to be able to plug infinity into my antiderivative. That doesn't make sense, okay? All right, so if we actually want to confirm our suspicion, right, that this area is infinite, then we're going to have to get a little bit clever, right, about how we approach finding this area, right? We can't just do it easily with just a straightforward definite integral. So here's what we're going to do, all right? I am going to, let's change the problem just a little bit, okay? We can't find the area all the way from 1 to infinity. So what I'm going to do is let's cut off this area at some value along the x-axis. So we'll still start at 1, right? But we'll cut off the area at some value. I'm just calling it b along the x-axis. But this will be a finite value along the x-axis, right? Okay. So for instance, I could let b be 10, or I could let b be 100, or I could let b be 1,000. Now, once you choose a specific upper limit for this definite integral, then of course you can evaluate it, right? And then, so we'll evaluate this definite integral for certain choices of b here, and then we'll let the b get bigger and bigger, and if the b gets bigger and bigger, we're hoping that we will get better and better estimates, right, for this the area of this unbounded region, right? So this is a very typical idea in calculus, right? I'm going to choose a specific value for b, and then I'm going to let the b get larger and larger and see what happens, right, to the area as the b gets larger and larger, right, as I get further and further out along the x-axis. All right, so let's do that here a few times, what I just said in words, right? Okay, so let's start here by letting b be 10. In other words, I'm going to find the area under the curve 1 over x, starting at 1 and going up to 10. So that's, you know, a little ways out the x-axis, right? So I'll get the area under the curve here from 1 to 10. Now that's not going to be my entire area, right? Because my entire region goes all the way out to infinity. But that region gets pretty thin, right, as you go further and further out the x-axis. So maybe this area will be close to that unbounded area, right? Well, let's see what that turns out to be. So let's try to evaluate this definite integral. And this is really easy to evaluate because the antiderivative is really simple here. You know this, right? The antiderivative of 1 over x is the natural log of x, right? Actually, it's the natural log of the absolute value of x. But I can drop the absolute value bars, right, because these x values that I'm using here from 1 to 10 are all positive, correct? So we just have natural log of x here evaluated from 1 to 10. That would be the natural log of 10 minus the natural log of 1. And natural log of 1 is 0. So this is really just the natural log of 10, which when you do this in your calculator, you're going to see that turns out to be 0.230. Okay, so I'm sorry, 2.30. So let's kind of remind ourselves in the picture here what we just calculated, right? So if we go, if we find this area all the way out under this curve, right, all the way over here to 10 on the all the way over here to 10 on the x-axis, that area turns out to be about 2.3, right? Okay. And so that's not the total area under the curve, right, all the way out to infinity. But again, as I mentioned, because this curve starts getting really close to the x-axis, right, even though it doesn't touch it, this curve starts getting really close to the x-axis. This area gets really thin, right, gets really skinny as you go further out the x-axis. So probably the area from 1 to 10, right, might be pretty close to the area from 1 all the way out to infinity. Okay, maybe, right? All right, now, but of course we can get a better estimate, right? So again, here's the way calculus works, right? We can get a better estimate, right, by picking a value further out along the x-axis, right, and then finding the area from 1 to that larger value. So you might change that a b value from 10 to 100, maybe, for instance, right? So let's try that, right? Okay, so let's choose this b value to be 100. In other words, let's find the area from let's find the definite integral from 1 to 100 of 1 over x. Well, that if you evaluate the definite integral from 1 to 100, just like we did from 1 to 10, you get that definite integral is the natural log of 100. And that turns out to be 4.61. So if you go from 1 to 10 along the x-axis, beneath that curve you have an area of 2.3. If you go from 1 to 100 along the x-axis, the area beneath that curve is 4.61. All right, well, of course, there's no reason to stop at 100, right? We can pick larger and larger values for b. These definite integrals are easy to evaluate, right? So we can pick larger and larger values for b, and let's see if we see a pattern, right? If these area values start to converge, right? If they start to converge, if we start seeing a pattern where they move to some specific value, right, then we'll have an idea of what the area under that curve would be all the way out to infinity, right? But if they maybe if they don't converge, right, then maybe we're correct. Maybe the area is infinite. So let's see what happens here. So let's pick b to be 1,000. So let's find the area from 1 to 1,000 beneath that curve. And again, that's easy to find. It's just going to end up being the natural log of 1,000 if you do the integration. But natural log of 1,000 turns out to be, check it on your calculator, it's 6.91. Well, let's get really ambitious here. Let's jump from 1,000 all the way up to a billion, right? Okay, so why be shy here? So when you find the area from 1 to a billion, now a billion is pretty far out the x-axis, right? But it's still a long way from infinity on the x-axis, okay? But if you find the area under that curve from 1 to 1 billion, you end up with natural log of a billion, and my calculator says that is about 20.7. So do these area values appear to be converging? So you have 2.3, 4.61, 6.91, 20.7. I don't see a pattern there at all, okay? I don't see that these numbers are really sort of be moving to some sort of fixed value. I don't see that pattern. So I'm thinking, I mean, these numbers just appear to be getting larger and larger, right? They don't appear to be converging to some specific number. So I think that kind of gives me an idea that maybe I was correct. Maybe we were correct, right? Maybe the area beneath this curve, right, from 1 to infinity, maybe this area really is infinite, right? Okay. And again, so that would be comforting, right? That would tell us that our intuition is correct, right? This is an unbounded region, so it should have an infinite area, right? Okay, that makes sense. All right, now look, this process that we just went through, right? We've gone through processes like this several times in the course, right? Where we're picking, here in this case, larger and larger values for this upper limit of integration. What we're really doing is a limit process here, right? I mean, we have terminology in calculus for this kind of process, right? And so, so let's write this process that we just went through, right, using the terminology of calculus that we already know, right? Okay. What we were really doing was we were trying to find the limit, right? As this upper bound gets larger and larger, as this upper bound goes to infinity, right? of this definite integral, correct? We were choosing larger and larger values for b. We were evaluating the definite integral, and we were seeing if those areas converge to some specific number, right? So, in other words, we were trying to compute a limit here, correct? And so we can express that idea, right, using our familiar limit notation from calculus. But now, once you've expressed this process using this limit notation, then it becomes much easier to see what's happening, right? Because you know what the definite integral from 1 to b of 1 over x is going to be. We already discovered in those prior examples, right, that that's just the natural log of b, correct? That's just going to end up being the natural log of b. So what we're really doing here is trying to compute, what's the limit as b goes to infinity of natural log of b? So as b gets larger and larger, what's happening to its natural log? And the answer is the natural log is unbounded, okay? As the input gets larger and larger, the natural log also is going to get larger and larger. It is going toward infinity. So this limit is really infinity, and that means that the area under that curve from 1 to infinity really was infinity. So we were correct, all right? This unbounded region has infinite area beneath it from 1 to infinity, okay? I mean, that makes sense, right? It's an unbounded region, so the area should be unbounded, right? So that's great. So see, we were able to use our knowledge of calculus now to confirm our intuition, right? Our intuition is correct, right? The region is infinite, or the area of that region is infinite. All right. Now, however, okay, all right, here's where our intuition is going to get confounded, all right? Because, again, as I mentioned, infinity is a much more slippery concept than one might think, all right? So I'm going to show you another example now, right? Okay, and here things are not going to work out like we expect. So now we want to find the area beneath this curve, e to the minus x, for x bigger than or equal to 0, but notice no upper bound on x, right? Just x bigger than or equal to 0. So this area also is going to be unbounded. Let me show you a picture of this area. It kind of looks like the area below 1 over x, all right? So this is the curve. This curve is e to the minus x power, right? Okay, so notice it's dropping down to the x-axis, but it doesn't touch the x-axis. E to the minus x does not touch the x-axis. It has no x-intercepts, all right? And we're going from, in this case, instead of starting at 1, we're starting at 0, and we're going, again, out to infinity, right? So what's the area of this unbounded region? That's what we're trying to discover. Okay, so we can express that as a definite integral, right? But we cannot evaluate the definite integral directly. So as a definite integral, that area, of course, would be the definite integral from 0 to infinity, right, of this curve, e to the minus x. And remember, this is called an improper integral because one of the limits of integration is infinity, right? Okay. So, so we're thinking, right, that that should be, when we evaluate that improper integral, right, we're thinking we should get infinity, correct? Because this region is unbounded, right? It gets thin. It does get skinny here over on the right-hand side of the x-axis, but this curve never touches the x-axis, so this region always has some area all the way out to infinity on the x-axis. Okay, there's always a little thin strip there of this region all the way out to infinity on the x-axis. All right, so how do we evaluate this improper integral? All right, so the trick to evaluating an improper integral, just like we did in the prior example, is always the same. Okay, you're going to set it up as follows. All right, so instead of using infinity as as one of your limits of integration, right, see, that's what makes the integral improper, is it has infinity for one of the limits of integration. So instead of using that infinite limit of integration, substitute for that limit of integration a fixed value b. You don't have to use the variable b. You can use any variable that you want, but here I'm using b again. All right, so put a b there in place of the infinity, and then look at what the limit is as that value b goes to infinity. Okay, and the reason that you want to substitute the b for infinity is so that you can carry out the definite integration, right? Okay, and then once you've carried out the definite integration using an upper limit of b, then you think about, okay, what happens to that expression when b goes to infinity? All right, let's try this here and see if we can do this. So to find, so you just ignore the limit for a moment, right, and find this definite integral, right? The definite integral from 0 to b of e to the minus x. Okay, so I'm going to do this by, I need to do this by substitution. So let's, I'm going to substitute u for minus x. So that means that du dx is equal to minus 1, which means that dx, right, is minus du, or I don't know, I guess if you want to, you can write it as du over minus 1, something like that, right? Okay, so again, I have to carry the limit along for a little while here, but I'm not actually going to evaluate the limit until the end. So I have the limit as b goes to infinity of 0 to b, right, of the definite integral from 0 to b of, and now I'm going to write this as e to the u, and then du, right, and then dx, which is du over minus 1. But this minus 1 we can factor out, right? So we will factor that out. So I have the limit as b goes to infinity of, let's see, this is going to be minus now, right, the definite integral from 0 to b of e to the u du. And it's now easy to evaluate that, right? Because the antiderivative of e to the u is e to the u, right? So I have the limit as b goes to infinity of minus, and then what? E to the u, right? Evaluated from 0 to b. Okay, so see, notice I have, there's my antiderivative. The antiderivative of e to the u is e to the u, right? And we're going to evaluate that antiderivative from 0 to b. Don't forget this minus sign here is here though, right? Okay, so let's see. We have the limit as b goes to infinity of, let's see, what is this? When you plug in when you plug in the upper limit, right, you get e to the b, right? Okay, and then when you plug in the whoops, I got ahead of myself there, right? Okay, whoops, let's back up a minute. I forgot to undo my substitution, right? I still have u here, okay? So before I actually plug in my limits of integration, I have to undo my substitution. And remember that u was e to the u was minus x, right? So I have first let's rewrite that e to the u as e to the minus x, right? And then that's evaluated from 0 to b, okay? All right, so now let's do it. So now we plug in the b, correct? So I have minus, and then e to the minus b, right? Okay, and then minus, so I plugged in the b, and then I have minus e to the minus 0, right? And don't forget this minus sign is still there as well. Okay, so let's simplify that now. a little bit before we try to evaluate the limit. So it looks like I'm going to get here, when you multiply through this minus sign, I get minus e to the minus b plus, right? Minus and minus is plus. And then e to the minus 0, well, minus 0 is still 0, and e to the 0 is 1. So it looks like I get 1 here, correct? But e to the minus b, I can rewrite that as well, because I can take the reciprocal, right? So I can write this as minus 1 over e to the b positive b power plus 1. Now I'm ready to evaluate the limit. Okay, so I've got my my definite integrals simplified, right? Okay, it's minus 1 over e to the b plus 1. And now I'm going to think about what happens to this quantity as b goes to infinity. Well, look, as b gets larger and larger, right? As b gets larger and larger, e to the b is also going to be getting larger and larger, right? So you have 1 over a really big number here. 1 over a really big number is essentially 0. So this first term is going to turn out to be 0, right? As b gets large, e to the b will be getting large. So 1 over this really large number is going to be 0. So you end up with minus 0 plus 1, and that turns out to be 1. Wow, okay? Not infinity. All right, so see, our intuition is been confounded here. The area beneath this curve, okay, from 0 to infinity is not infinity. In fact, it just turns out to be, strangely enough there, the number 1, okay? So there's really only, wow, that's cool, there's really only one square unit there, 1 square unit of area beneath that curve all the way out to infinity. Wow, I really like that. How can that possibly be, right? Okay, because you have an unbounded area. This area is unbounded. It keeps extending all the way out to infinity. So the further to the right you get, the more area you get. But no matter how far to the right you get, you still don't ever get an area bigger than 1 square unit. Okay. So this is what I was telling you, right? Our notion of infinity, sometimes our intuition about infinity is imperfect. Okay. Here is an example of that. We would think that this unbounded region, because it's unbounded, the region goes on to infinity along the x-axis. We should think its area is also infinite, but its area is not infinite. Its area, it turns out to be exactly 1. Okay, so that's neat, right? So as I mentioned, right, this topic of improper integrals can teach us a little bit about how, a little bit more about how infinity really works, right? Okay, because our knowledge of infinity, as I mentioned, is not perfect. All right, so we've got some more examples to look at with improper integrals. All right, but that's the start of the process of how we evaluate these so-called improper integrals, or how do we find areas of infinitely unbounded regions. Okay, so I'm going to stop there now for today, and we'll resume on Monday. We have some more examples with improper integrals, okay, on Monday before we get into our next big topic. So I want to say good luck to you on your test, right? You should be in the middle of taking your test, or maybe you already took the test and you've submitted that to me. So I hope you did well on that, and stay safe over the weekend, right? Until I see you again on Monday, right? On Monday. So remember to wash your hands and wear your face mask when you are around people, right? Don't forget to do that. Okay, and I will see you then. Bye.